base station, I think around 300 meters from the place where they want to place the energy harvesting, and the FM tower is around 3 kilometers. So you can see there the three, four, five band, and you can get the energy. I think very good around 10 dBm as GSM 900. So based on this survey, energy survey, they have designed multi-band antenna for GSM 900, 1800, and 5G and Wi-Fi. So for this one, four band, they designed the uh, multi-band antenna, and for FM to receive the FM signal, they designed a monopole type antenna. So they have did different like RF combining and DC combining, and then they have the hybrid combining. So hybrid combining is the best for this example because they propose a smart energy harvesting tree. So you can see each antenna has the four antenna, four side, and one is the FM antenna. So they can receive the power from one antenna. Total power is 315 millivolts for one antenna. So if you combine all, you can get a lot of power. This is the ambient energy power, received power. So if you're using the dedicated source, you can get the 3 volt, 2.5 around volt. So this is like a 3D antenna. You can receive the energy from all directions. So these are the ambient RF energy sources. Because if you look at the energy from different sources, you have the Wi-Fi, RFID readers, and GSM tower, mobile tower, 5G or radar, satellite. There are so many, and router and laptop also. Because in the environment surrounding, there are the different type of wave, like linear, circular, and slanted, vertical, horizontal, random polarized wave. So the polarization is very important for designing the energy harvesting system. If you look in the environment is the isotropic type of the energy. Energy is everywhere, and the wave polarization also arbitrarily. So how to design the antenna to capture as much as energy? This is the challenge for antenna designer. So if you look at there are the different type of antenna. If you look, this one is the monopole type antenna, and this is the like can receive the power from all around. And this is the circular polarized, also monopole type antenna. And this is the metasurface based harvester. Metasurface means you have the large surface, you can receive the more energy and convert to you can combine by like DC combining or like. So if you look the dual polarized antenna can receive the power almost all polarized. The slanted also can receive around 50%, but can receive almost all polarized wave. And this is the isotropic antenna, also like a omnidirection in this direction and this direction also. So this antenna is like a isotropic, can receive the energy from all directions. And this is the metasurface based circular patch antenna. This is the directional antenna, only the receive one direction. And this is the dual band antenna, high gain, can receive high gain. And this is the, if you look the conformal type, and this one also can receive energy from all direction and combine with DC combining. This is the high gain circular pole antenna, and this is the dual circular polarized antenna, and can receive the almost all energy and waves. with different polarized wave, slanted, unpolarized also. And this is very interesting, 6 dual band, dual circular polarized antenna, rectina, and receive 6 band with all other like slanted also, all kind of wave can receive. And this last one is the hemisphere monopole rectina type array. So they propose like a power bank. So you have a lot of monopole antenna. They put the hemisphere and then DC combining, first AC combining to and then DC combining, and you can charge you can use as a power bank of this type of structures. So these are the some other type of antenna like multi-band patch antenna. So this antenna designed for GSM 900, GSM 1800 and Wi-Fi and 3G. And this is the dual band to fractal antenna and GSM 900 and Wi-Fi band. And this is the dual band, dual inverted F antenna. This can also receive 2 bands, both the GSM 900 and 1800. And this is a DRA antenna, bow type DRA antenna. And this is a very wide band and cover from 1800 to 3G. These are the reflection coefficient. You can see the different patch antenna is this one, the 4 band, and fractal antenna have dual band, this dual band, and inverted F antenna is dual band. And if you look at the DRA is a very wide band, this one, and FNC also very wide band. So these are the antenna configuration and the radiation pattern. If you look at the monopole radiation pattern, the energy can receive in all directions, but you cannot receive from this direction and this direction. If you propose the directional antenna, only energy can receive in this direction. So if you have the dedicated source, so you can use the directional antenna, so you can receive maximum power. So if you don't know the power, the dedicated where the power source or ambient source, so you have to use the like this hemisphere radiation pattern. You can receive the energy from all directions. If you design the hemisphere beam antenna, so gain will reduce. So if the power is low, then you have to go the 3D antenna. So if you have the 4-5 dB gain antenna, you can put the in 4 direction and one is top. So you can receive large energy from all directions. So if you know the source, dedicated source, so you can use the high gain antenna like this, where you can receive more energy. So antenna radiation pattern is very important for energy harvesting system design. So now next is the polarization. What is the polarization effect? So in the antenna is different type of polarization like linear, circular, or elliptical, vertical, and horizontal. If you look this elliptical, uh, sorry, if you design the circular polarized antenna, so both component, the maximum or minimum should be same. Then you can get the AR is the 1, means 0 dB. So this circle becomes this ellipse becomes a circle. So we call the circular polarization. So one of the component is 0, it becomes the either vertical and horizontal polarized. Like OA, this is the vertical polarized, and this is the horizontal polarized. Then circular polarized also have the right hand or left hand. So for receiving is no problem if you have the right hand circular polarized antenna. Only left hand cannot receive by the right hand circular polarized antenna. Otherwise, all other type like vertical, horizontal, slanted, all can receive. So this is a very good table to understand the polarization effect. Like the wave polarization in the environmental, these are the wave polarization in the surrounding environment, and this is the receiving antenna for energy harvesting. So if the wave in the environment is the what horizontal polarized, so horizontal antenna can receive 100%, and like a dual polarization antenna also can receive. And if you look the uh, circular polarized antenna can receive 50%. So if you consider the polarization in the environment is the random, so the dual linear polarized antenna or dual circular polarized antenna is the best. Or at least all wave can receive 50%. Like if you have the horizontal, vertical, or slanted, or circular, or right hand or left hand circular. So the dual polarized antenna. This is the dual polarized antenna can receive at least 50% all waves, and dual circular polarized also can receive. So dual circular polarized and dual linear polarized almost same for energy harvesting system design. So this is very important to for antenna designing. The polarization is very important. So next I will discuss the circular polarized antenna design. So generally three type of the feeding structure used in the circular polarized antenna design. One is single feed. Single feed is very simple, but is the problem is the narrow band. And other is a dual feed. Dual feed all is can get the wider bandwidth, but you need some circuit. That's why the structure is the larger size. Other is the sequentially rotate. If you rotate sequentially, right, 0, 90, 180, 270, you can get the circular polarization, very good circular polarization. But the problem is the size. So if you design the compact antenna, circular polarized antenna, so you have to go for single feed. Generally, the rectifier have to connect with single feed. So for energy harvesting, single feed antenna is better. So circular polarized microstrip antenna. This is the cross section of the typical microstrip antenna. This is the substrate and this is the radiator. For if you have the linear, if you have the nearly square patch antenna, and if you feed the diagonally, you can generate the two mode, 0, 1 and 1, 0. For circular polarized antenna, there the condition you have to have generate two orthogonal mode with 90-degree phase shift. You can generate the circular polarized. So you can see here, one is the 1, 0 mode and 0, 1 mode. And this is the return loss of this one. You can see one this mode and one this mode. So this is the condition for circular polarization. You have to have two orthogonal mode with almost equal magnitude and 90-degree phase difference. This is the condition. So if you look at circular polarized frequency means uh, low axial ratio, lowest axial ratio. For perfect circular polarization, axial ratio should be 0 degree. So if you look, the minimum axial ratio is the average of the two mode frequency. One this mode fx fy. If you divide it by 2, you can get the minimum axial ratio. And this is very simple. If you design single feed, you have the nearly square patch, slightly the change the L or W and feed in the diagonal direction, you can generate the two mode. And same in this case, You just cut the corner, slightly cut the corner, one of the diagonal direction, and feed in the orthogonal direction, you can generate two more. If you cut any like a rectangular slot at the center, you feed orthogonal direction, you can generate the two more. You need some asymmetry to generate the two mode with single feed. It's very simple. So based on that, we have developed, I think, lot of antenna in last 10 years. So this is just we feed in orthogonal direction here feed, and then we created the one cross slot in one of the orthogonal direction, so we can generate two mode, one this and one this. So we, very easy to generate circular polarization. And other one like to smaller circle in other all different radius circle in different diagonal direction, and you feed the orthogonal direction, you can generate the circular polarization. Very simple. So other one is if you add the different circle in corner, you feed orthogonal direction, you can get. So based on this concept, we designed a lot of antenna and we published. And I think the citation of this work, because this is very simple, very high. I think more than 200 citation on this. So I will discuss more detail in this antenna because this is very interesting. Based on the slit, asymmetric slit, we generated the circular polarization. For slit or slot, the one important is we can reduce the size of the antenna and we can generate the circular polarization. These are two advantages. The E shape and the cross shape and this the cross shape and this the slit, all same concept. So this is the circular polarized antenna with taper slit structure. So this is the proximity field, this is the ground plane, and this is the feed structure, and this is the radiator. So this is the octagonal patch, and we just cut the asymmetric slit in the patch to reduce the size and generate the circular polarization. If you look at this slit, this is the changing like this percentage change means 1.3 percentage change in the this slit length. So we can generate the circular polarization. This is the ground plane and this microstrip line. This line. This is very simple, and the one of my FYP student did this work. Very good work. So if you look at, if you compare without slit and with slit, frequency difference. This is the 1.04 gigahertz, and we can bring this one down to zero point 0.9 gigahertz. So this is the reduction of the frequency. Means you are designing the electrically small antenna. These are the some equation you just feed in the CST. We can optimize the antenna for circular polarization. Very simple. So this is the electric field distribution. If you look, the field change with change of the phase. If you look this 0 and 45 and 90 and 135. So this is rotating like a circular. So to check the circular polarization, this is the very good method to check. Just to add the like 0, 45, the wave change, the electric field change with the change of phase. And this is the surface current distribution and axial ratio. You can see the surface current is very, majority of the surface current is around the slit and very symmetrically. So based on this symmetry, we can get the very wide beam. Means the axial ratio beam width is almost upper half sphere, like 180 degree. You can see here around minus 90 to plus 90, and both cut the XZ and YZ. And this is the some parametric study, we change the slit length, this length vary like to 35.4 to 37.4. You can see the axial ratio is still less than 3 with variation of the TM. But we keep the axial ratio less than 3 and we can tune the frequency with desired frequency requirement like using 900 or you can change the frequency with other. Gain is almost changed with change in frequency. And this is the M means the change in the length, this length to generate the circular polarization. So if you change the M in percentage, this is the percentage. So the return loss also change and axial ratio also change. So this is the change the asymmetry. So for best axial ratio, 1.3 is the minimum axial ratio. For best circular polarization means it should be 0 dB. And this is the D means the slit width on the outside, and this D is this one. So this is also have a slightly effect, but not much. But keep the axial ratio below the 3. And we have prototype and measure this and compare with simulation. You can see this is the prototype antenna, and this is the reflection coefficient is good agreement, and this is the axial ratio simulated and measured, and this is the gain of the antenna. So after that we have design. Oh, this is the radiation pattern, major radiation pattern. This for circular polarization, we have the special measurement of the radiation pattern because we call this one. You can see the ripple, right? This ripple represents the axial ratio value. Means the difference between two ripple like this. This represents the quality of the polarization, circular polarization. Means minimum is the ripple, the best is the circular polarization. Means no ripple means the 0 dB. So here is the very small ripple, means the acceleration is very good. And if you look this from minus 90 to plus 90, almost within 3 dB, we can say the upper half of the sphere is we can get the 3 dB acceleration bandwidth. So this antenna can receive from energy from all directions with different like vertical, horizontal polarized, circular polarized base in both cut like XZ and YZ cut. So this is very important for circular polarized antenna. The axial ratio should be minimum in all directions. Like this, the below, the acceleration is not good. After that, we have designed the rectifier for this antenna. So we use the voltage doubler circuit configuration, and then some composite right left hand metasurface transmission line to design the matching circuit. So for left hand circuit, we use the lump component, and for right hand circuit, we use the microstrip line to design the rectifier circuit. So these are the some values for voltage doubler, the frequency, impedance, input power, load resistance, and others. We have designed the rectifier and connected with the antenna, and this is the reflection coefficient, and this is the efficiency measure and the simulated. You can see the big difference in the measure and simulated efficiency due to the because this is the in-house fabrication student project, and the matching between the antenna and rectifier is not so good. So the efficiency is very low. Major efficiency is very low, around 40%. So next, we have developed the dual band efficient circular polarized antenna for energy harvesting. So this is also same student have developed, and just to use the same antenna for uh, GSM, and we added the Wi-Fi antenna at top of this one. So this the overall structure is very compact, because if you look, this is the feeding line, and this is the Wi-Fi antenna directly feed with Wi-Fi antenna, and this feeding line also electromagnetic coupled to the this GSM pair. So overall structure is very innovative, and this structure we have also patented, filed the patent. So these are the dimensions, some dimension, and this is the Wi-Fi pattern radiator. We use the circular for circular polarization. We create the circular slot smaller and bigger in diagonal direction, and feed here. You can see the feed is here, so we can generate the circular polarization. So in this case, the same, we use the uh, smaller, bigger like this. So we can generate the circular polarization, changing asymmetric slit to generate the circular polarization. These are the some equation. You just put in the software the equation, and you can get this circular polarization design and at 900 and 2.4. So if you look the side reduction, if you create the slot in the patch, your frequency will down, tip down. So it means you have the electrically small ampere. In same like in this case, you can shift the frequency from 1.5 to 900. So this is the electric field. You can see the electric field is moving circularly with change in phase. It means there is a circular polarized antenna. And you can see here the field is moved in the Wi-Fi band. These are the current distribution, both GSM band and the Wi-Fi band. You can see very symmetrical current distribution uh, at the GSM and Wi-Fi band. Wi-Fi band is the top. You can see the only the current distribution on top. This is some parametric study of this antenna, dual band antenna. You can see both band. If you change the slit, uh, slit variation, like this percentage variation, like clockwise, both band is changed due to, because Wi-Fi antenna ground plane, the GSM antenna is the ground plane of the Wi-Fi antenna. So if this something change in the GSM antenna, so Wi-Fi antenna impedance also change. So you can see the return loss also change with change in the GSM antenna. So you can see here both bands can get the minimum axial ratio at 6.25 m. Means percentage change in the length in clockwise direction from the center. And the gain variation also changed with the m. And this is the rotation of the slot. Because we have also checked what is the effect of the, if you rotate the slot and like 35 to 55, you can see the only Wi-Fi band is changed. And around 45, we can get very good matching and acceleration. And this we have also checked the substrate thickness change, substrate thickness effect also in both bands, because the GSM antenna is the ground plane for the Wi-Fi antenna. So that's why both band is effective. If you change this substrate thickness around 5.6, you can get the best result, both band. Best result means should be minimum acceleration. So we have fabricated this antenna, measured and compared with the simulation. You can see the very good agreement measured and simulation, and we can get the ratio. These are the radiation pattern. You can see again the very nice acceleration with minus 90 to plus 90 in both XZ and YZ cut. And this is a 910 and this is a 911. Because this measurement is different. In the transmitting antenna, always rotating, and the major antenna measure. So this determine means we have the different polarization. So in different polarization means all directions we can receive uh, waves in like vertical, horizontal. So this is the Wi-Fi band radiation pattern. You can see this and the Wi-Fi band is not so good in minus 90 to plus 90. So that this beamwidth only limited in around minus 30 to plus 30, around 60 degrees. So this antenna is good for only the 60 degree because this one the aim of this antenna design is because the Wi-Fi router only on the roof, so only this one can receive from the top. So this is the major performance of the dual band circular polarized antenna. 10 dB return loss bandwidth, 3 dB acceleration bandwidth, with gain, and operating frequency size. Size is very small. For circular polarized antenna, axial ratio is very important. Axial ratio bandwidth and beam width. So we have also compared with other antenna. Our antenna have a higher gain compared to the other like the dual feed need large size and some power loss in the feeding configuration. So for this antenna, we have also developed the dual band rectifier structure, and we have used the same technique. We use doubler circuit and uh, composite right hand left hand based impedance matching circuit. So this is the dual band impedance matching circuit. You can see the microstrip line used for right hand, and left hand we use the lump component. So these are the some values for the dual band 900 and 2.45, and this is the reflection coefficient of the rectifier at 0 dBm. And these are the measured rectina efficiency. You can see again the measure and the similarities have big difference due to the matching and some fabrication tolerance. So next is I will go very next we have proposed smart home sensor charging via wireless power transfer. So if you look at the smart home, we have the lot of sensor and we know the places. We know the butter matrix. If we have the 4x4 butter matrix, we can generate the 4 field. So we can focus the 4 area in the smart home where the sensor is there. So based on that, we can charge the sensor wirelessly because this is the whole system. This is the wireless power transfer, and then sensor have the uh, energy harvesting system unit to harvest the energy from these antenna release. So for this one, first we have designed the miniaturized coupler, You can see this is the coupler and this is the fabricated coupler, and we have measure. You can see here only we can get the 3.5, means 0.5 is lost. Uh, we have to, and then this the difference is the 90 degree. So port 1 is the input, port 2 is isolated, and port 3 and 4 we have the power division 3 dB. We can get the around 3.5 and 3.5 because the 5 dB is lost. And you can see the 90-degree phase difference between. And for butter meshing, you need crossover. Crossover means you can pass the signal without distortion. So we have also developed the crossover at 2.4 gigahertz. You can see here for crossover means zero phase difference. And the input power port 1 is the input port, port 3 is the through port, means the signal should go through. The 1 3 should be 0, but we I think around 0.5 dB loss. So you can see here 0.5 dB loss. And then we combine all. These are the this is the crossover, and these are the 4 hybrid coupler. We combine and develop the 4x4 butter matrix. And this, if you put the input port 1, port 2, port 3, you can change the phase in 5, 6, 7, 8. The phase change -45, 135 like this. So you can see here the very wide band S11, S22, 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 and this is the power couple power. Should be around to 60 dB. 60 dB. But we have get around -8 dB. 2 dB is lost because the circuit, coupler circuits and crossover. So, and for this one, we need to antenna design for antenna. So for uh, antenna, we use the E-shaped slotted circular polarized antenna. E-shape means we can reduce the size and generate the circular polarization. And the E-shape is in this direction, in the orthogonal direction, and the feed is in this direction. So based on that, we can generate two modes, and we can reduce the size, and we can generate the circular polarized. There are two advantages for E-shape pulse. And this is the electrical distribution. You can see it changes the phase in circular manner, and we fabricate in measure. And this the four antenna we placed very close to get the very good beam. Otherwise, we have to grating lobe. To avoid the grating lobe, we placed a very close. I think the distance between the antenna is 0.29 lambda. So overall system very compact. So we connected the four antenna with butter matrix to generate the four beam. You can see here the four beam. We measure and simulated very good agreement. The beam angle is the -5, 65, -55, 20. So if you connect the simple S4 SP4T switch at the butter matrix, can use the electronically change the beam in different direction, because you need to change the sensor in different other 4 different directions. You can change like 1, 2, 3, 4 like this. So for
Hello, sir. Hello,
yeah,
sir.
yep.
Can we speed up the presentation a bit because
Okay.
the time has been exceeded a bit?
Okay. So for charging the sensor, we developed the rectina, circular polarized antenna. This is the toss shape circular polarized antenna, and then connect it with rectifier. For this one to harvest the energy from the butter matrix. These are the system to test the system. You can see the 4 antenna here, and this is the harvester. So based on the measurement, we can get the 30 milliwatt in 4 different directions. And we have also compared with the simple formula and our measurement. You can see the very good agreement. So almost finished. So I have to discuss the energy harvesting system and applications and sources and wave polarization in the environment. And I have also discussed the different antenna configurations for energy harvesting, and I have also discussed the detailed polarization. And I have presented the compact wide beam circular polarized antenna for GSM band and Wi-Fi band, and I have demonstrated the wireless power transfer system for smart home. Okay, thank you so much, everyone.
Thank you, sir. That was a very well researched and very informative presentation. Sir, we have some questions in the chat box. I will read them to you. So some of the interesting questions. Some of the questions I think you can get from Google itself. So the questions are: is there any terahertz band that is suitable for harvesting purposes?
Terahertz, I think we don't have the source, right? Very difficult to get.
Yeah, exactly. There are no sources in terahertz band, right?
Yeah,
right
yeah.
Now?
How can I harvest the energy?
Okay, so I think it is not possible in that band right now, I think.
The 5G can. I think 5G.
Okay, so the next question. 5G is in the gigahertz range, right?
Yeah, yeah.
Okay. So I will tell the next question. It is, while designing ambient RF retina, should we optimize load to ambient power and then design a matching network? So it's a practical question. Or should we optimize the load for best power and maximum efficiency?
No. This is the.
Can you comment on that?
Because the matching circuit depend on the frequency, power, and load.
Okay.
So if you change any, the matching is changed. This is very, I think, challenging part, matching circuit. Because if you have to consider the power only or load only, you can optimize at particular load or power. You cannot if you change the frequency or power and your load is fixed, you have to fix one and then optimize. If you change one, then the matching is changed.
Okay, so for different frequencies, we should fix different loads, right?
Yeah.
Okay. And the next question is, how to design feed network for these antennas? Is there a special way of designing feed networks for these antennas? Or is
which antenna?
Is it like conventional?
Oh, this is a simple coaxial feed.
For the energy harvesting antennas, I presume.
It depends, you need a wide band or narrow band, or it depends on the requirement. If you have narrow band, you just use the coaxial feed.
Okay, sir. So I think it can be designed according to the application. And the next question is, what type of antennas are most suitable for energy harvesting in wearable device? So is there a specific kind of antenna that can be used in such applications?
Oh, wearable device. I think the monopole type antenna is best, or inverted F antenna is good for the wearable device.
Okay, so I think that has answered that question. And the next question is, while designing ambient RF retina, which approach is better in your opinion? I think, okay, so this was the earlier question. It was related to the load and power matching. So it's the
I
same
think
question.
if you design
Sorry.
the efficient energy
And
harvesting system, you have to survey the power density.
okay.
What is the power available power? Based on that, you can design the efficient. Because if you have the power, high power, then you no need to very high gain antenna design. If you have low power, you have to design high gain antenna, like a sector antenna, 3D antenna. Then you can increase the power. It depends on the power, I think, available power.
Okay, designing a high gain antenna, it will increase the form factor of the antenna too, right?
Yeah, yeah.
So, so I have one question. So this was a really good presentation and it had lots of information and the resources that we could use. So I would like to know about some definitive resources and material that students can use to learn more about antenna harvesting, energy harvesting antennas and how to design these antennas. Is there any, can you give me
I think for
some
energy
recommendations?
harvesting is very low cost because the diode is very cheap, not expensive, and you use the FR4 substrate. If you have the
Okay.
mobile tower or the TV tower very close, you just design very large antenna. You can receive some power, right, and then use for
Yeah.
some temperature or something. This is a very good student project also.
Is there some resources or material that we can refer to design these antennas?
You can use RF4 is very RF4 substrate very cheap, right?
No, I mean the textbooks. Textbooks.
Textbook.
Yes,
Oh,
yes.
textbook. I think still you have to wait next year. Next year will come one textbook.
Is there a name for that we can note down?
We have I think what is the name? Another antenna for energy harvesting systems, something like this.
Okay, so this field is really new, right? So I
Yeah,
think
I
there
think
is
this is need lot of research. Still 2 3 year. I think need a lot of research to get the power level high. Because now the wireless, the what is the base station increasing, right? 5G coming, then power level will increase. So maybe it's good for future this technology.
okay, sir. So I think everyone can take note. We have one more question, last question. How do we have to select the shape and position of the slot for a particular resonant frequency? I think that depends on the impedance matching. Okay,
The slot
okay. So
means for circular polarization, right?
yes, probably to get
Okay.
maximum energy harvesting.
Because if you have the square patch, you just select the slot in the diagonal direction and at lambda by 8 from the center.
Yes. Okay, sir. So that is the best method, best way
Yeah.
to select the shape. Okay, sir. So I think that has answered everyone's questions, and it was a really interesting and informative session. And
I
with
think I face some problem, some eco problem, some cannot concentrate.
no, sir, that it was solved 10 minutes, 15 minutes into the session.
Okay,
It
okay,
was because there were two, the, yeah, it was solved. It's all right.
okay,
We
then,
were able
okay,
to hear you properly.
okay. Thank you.
And yes, sir. And I would like to welcome the dignitaries of IEEE Kerala section who are there with us right now. So right now we have two former chairs of IEEE Kerala section, Dr. Anandan sir and Dr. Chinmoy sir. And then we have the current IEEE secretary, Dr. Arjit Mitra sir. And we also have the counselors and faculty advisors for IEEE SB chapters. I thank you, sir, for on behalf of all of them. And I would like to call Dr. Deepti Das Krishna, IEEE APS CUSAT chapter, CUSAT SB counselor, to say a few words. in gratitude to you, sir. Dr. Deepti Das Krishna, ma'am, can you hear me?
Yes, am I audible?
Hello.
Yes,
Hello,
ma'am, you're
Dipti.
audible.
Yeah, hello, sir. Good evening to the dignitaries present and the students, and very good evening to Nasimudin, sir. All of us recently would have seen some WhatsApp forwarded video about the wireless power transfer demonstrated in New Zealand, and with all the IoT devices coming up. So this sort of RF harvesting is relevant and futuristic, and we have the privilege of having Dr. Nasimudin, who is well known and who is very with a lot of work in this domain, and it's our privilege and that he accepted our request to do a session for this APS conclave, in spite of the fact that it is quite late on a Sunday evening at Singapore, and tomorrow being a working day for them. I think we should, thank him from the bottom of my heart. I thank him for accepting this and giving a fantastic presentation. I'm sure it would inspire more students, researchers to look at the challenges in this domain. Thank you very much again, once again. Thank you. Yeah.
There's a lot of participants, 75. Good
Yeah.
number.
So over to Edwin.
Yes,
yeah.
So thank you, sir, for coming. We are all really happy that you took the session.
Thank you so much, all. Thank you so much, all, everyone.
So for the next session, we have Dr. Sandeep Shangar Roy.
Good night, everyone.
Good night, sir. Thank you, sir. Nasimudin sir will be leaving us because it's quite late in Singapore. And for the next session, I'll be calling Subhana. She's the IEEE APS chair in Musaliar College, Trivandrum. I invite her to welcome Dr. Sandeep Chandra Roy to this podium. Subhana, can you hear me?
Yes, ma'am.
Yes. So you can give the bio and you can welcome Dr. Sandeep sir to the stage.
Okay. Good evening, everyone. I'm Subhana, APS student branch chair from Muslia College of Engineering. Now we have Dr. Sandip Sankar Roy as our next speaker. Dr. Sandip Sankar Roy, scientist in NRSC, is working in radio frequency and baseband system group. He joined NRSC in 2009 and working in the same organization till date. His current area of research is design of microwave antennas and waveguide structure, tracking feed and reflector antenna for LEO satellites. He is involved in installation of antennas in different ground stations within India and abroad. He is a team member for installing antenna at Polar Station in Antarctica. He is involved in different satellite missions like RISAT-1, CASA 2A, 2B, and RISOSAT-2. He is project manager for RISAT-2A and RISAT-2B mission. He is awarded ISRO Young Scientist Award for outstanding contribution in space technology in 2016. He is also awarded ISRO Team Excellence Award for his important contribution in installation of Polar Ground Station at Antarctica. His talk is on antennas for satellite tracking. Different tracking techniques are applied from early days of satellite communication. Out of these different tracking methods, monopulse tracking is more sophisticated mode of tracking. Tracking ground station antennas have some and different modes, with different optimization goals which have to consider separately. Maximum efficiency along with low site lobe level is desired parameter for some mode, while for different mode, sensitivity or tracking slope and maximum lock angle is the optimization goal. Several researches have been carried out to find out optimum feed for the monopulse. 4-element, 5-element configuration, multi-mode feeds are interchangeably used depending on stringent system specification, complexity, and cost effectiveness. Complexity in design increases when a single antenna aperture has to be used for different frequency band and design criticality mainly imposes in design of multi-band or composite feed. Frequency selective surfaces are often used to achieve multi-band operation in reflector antennas. I welcome you, sir, onto the dais.
Hello, sir. Can you hear me? Can you hear us, Sandeep, sir?
Yeah.
Yes, sir. So I would also like to call on Dr. Chinmoy Saha, sir, our former chair, Kerala IPS chair, to say a few words and welcome Dr. Sandeep Chandra Roy. Chinmoy, sir, can you hear me?
I hope my audio is okay today.
Yes, sir. Your audio is clear and your video is also clear.
Okay.
So over
So
to you.
yeah,
Yes, sir.
all the best for all of you. And as you will be seeing very soon, Sandeep is a very robust worker. He works not on very small antennas, but very big antennas with very high gain. You know that microstrip and small pinted antennas and some dielectric antennas, etc. You'll be hearing for many people. I mean, those are of course needed different kind of applications. But the sorry, the type of work that NRSC is doing, and I am also part of this journey due to ongoing collaboration and also Sandeep's research work in our group. So this talk will be very, very illuminating, I'm pretty sure. So all the best. Enjoy the talk. I'll be talking later on. Thank you.
Thank you, sir. Sandeep, sir, I think you can start the presentation.
Yeah. My presentation is visible to all?
Yes, sir. It's visible.
Okay. So I want to thank IEEE APS for giving me the opportunity. Good evening to the dignitaries present and all the participants. Today I will be talking about design, development and realization of ground station antennas for tracking of LEO satellites. So from the term, we have here ground station and LEO satellites and tracking. These three terms we are talking more. These are the striking of my presentation. So first of all, what is LEO satellites? So what are the types of satellite orbits that I will tell that satellite orbits are mainly three types of satellite orbits are there. First one is geosatellite. Geosatellite means that is constant to our earth, and they are 36,000 kilometer away from us. And then meo satellites means they are in between geo and leo satellites. So uh, they their distance is little bit more than leo satellites. And next is leo satellites. Leo satellites orbit the earth and it is very close to the earth. So uh, all the satellites having different applications. Geosatellites is mainly used for as a communication satellites, but nowadays it is finding application in remote sensing satellites also. Leosat and MEO satellites are basically GPS satellites, and Leo satellites. Leo satellites are actually, if you want to take a picture of the Earth, then these Leo satellites are used. They are mainly Earth observation satellites. Earth observation means you have to take a picture of the Earth. Then after that you have to first of all there will be a camera. Then that camera will take the picture, and that picture will be modulated, and then it will be converted to a higher frequency, and after that higher frequency you will give into the antenna on board, and then it will be transmitted back to the ground station. And ground station job is not only take the data from the or receive the signal from that satellite, but also to track the satellite. So these are the different satellites that ISRO has launched. Both geo satellite and leo satellites both are present in this picture. So these LEO satellites, they are actually sun synchronous satellites. Sun synchronous means they will they will follow the same local time. Suppose there is a satellite pass is and around 10 o'clock morning in Hyderabad, so next day it will come in and around 10 o'clock, so same local time. So that is sun synchronous satellite. So this satellites actually travels from north to south, and they stays very close to the earth so that they can take pictures. So pictures can be taken in optical domain, also in infrared domain, and also in microwave domain. Means it is will be a radar image. So in optical image means night you cannot take the picture. So there are certain applications where you cannot wait for the day, you want the picture at night itself, so that time my optical image will not work. Also there are if the cloud is more, then you cannot see the earth properly, so at that time this optical image will not work, so we have to move to the radar image. So these are the basic applications, basic satellite about LEO satellite. Now satellite visibility. Now if a ground station antenna is there, then from that if the antenna gain is more, then the visibility will increase. So these are the and with elevation also the visibility increase. Means if the antenna gain is more, then it can receive the satellite, can meet the link margin, and it can receive data from the satellite from a lower elevation. So with the with the elevation the visibility decreases. So you can see at 0 degree you can see the entire India and also some part of China, Pakistan, and like that. If you say 10 degree, then you just from Hyderabad I am showing the visibility, so you cannot see all the part of India, some part is left out. So like that we have a 7.5 meter antenna system, and we receive the data from 5 degree elevation. So this is the one satellite path. So this depends on how much you are covering. So different satellite will having a different swath. This is called this thing is called swath. So this strip is called swath. So as the swath increases, then the resolution decreases. So like the same thing, if you want to catch a wider thing, then your resolution will decrease. But if you want to catch a in a very small domain, so then your resolution will increase. So like that uh, for certain application wide range is required. For certain application like urban planning, cartographical thing, the swath requirement is less. So you want to identify buildings in urban area, so in that time you need a cartography application, you need a small swath and very high resolution. Now ISRO has launched Cartosat 3, and which is capable of 25 centimeter accuracy resolution is there. That means you can identify one point within 25 centimeter accuracy. So this is the basic block diagram of the total satellite communication system for LEO satellite. So it will take the image, it will from the payload, it will take the image. Then after that the payload electronics will be there. Then as the you know that this is in image will be in digital domain, it will be in pixel. Then from the pixel it will be converted to the it will convert to the analog domain. Then after that when it is comes to the analog domain, then data handler will be there, and it will modulate the signal to the higher frequency. Presently we are transmitting signal in S band, X band, and Ka band. And then after that it will be given to the RF transmitter. There will be SSPA sitting over it, solid state power amplifier, and it will then after that it will generate more power, and after that it will be given to the antenna system. Antenna system will having a gain, then PT into GT, that is the EIRP, effective isotropic radiated power, that will be sent to the ground. So when it receives at the ground, then at that time there in the antenna there is a feed system. So it is a Cassegrain antenna or prime focal antenna, reflector antenna. There will be a feed system. From the feed system, this electromagnetic energy will convert it to the electrical signal or RF signal. Now RF signal again it will be down converted, and after that again it will brought to the IF level, and then after that it will be demodulated. and after demodulation it will be given to the data engine system, and it will generate images. That images will be analyzed by scientists, and many information can be known. Now, what are the information we can get from these images taken from the satellite? So agricultural and soil application. Agricultural and soil application means the crop coverage and production estimation. Means if state approaches ISRO and they say that how much paddy is developed this year, so that's estimation we want. So that can be done with the satellite imaging. It will map the total, it will take create a mosaic of the total state, and it will say that this much paddy production is there. Like that, the land use and land cover mapping, waste land mapping, urban sprawl studies, and large scale mapping, and also forest and environment, how much forest cover is there, and if there is a forest fire. This is a big problem nowadays, that we are losing our forestry, and that can also, when there is the initial stage of the forest fire, if it can be predicted, then we can avoid the loss of forest fire. Then biodiversity, and also there is a application in potential water drinking. So there is some project in which it can be said that what is the potential drinking water zone, or where we have to bore for the well, like that. So, and potential fishing zone. So potential fishing zone is also one application. And also if some disaster happens, like in Vizag hudud happened, and like that. So if there is any cyclone or thing, then at that time how much damage has happened. So for assessing of that, that is also done with this application. So I told all these things because for what purpose the satellite data is being used, so that it can be known. So that one application I just want to tell, that this potential fishing zone. So fishing zones, what in which part of the sea, or which area the fish can be, fish are information can be sent to the fishermen, that this part is more probability of getting fishes. Like if it is a hot water and a cold water, so when hot water and cold water in the junction of that, there is a more probability of getting fishes. So that information is satellite gets the information from the imaging, and then it information is transferred to the fisherman or corresponding agency, and that agency will broadcast the information to the fisherman, and they will predict that potential fishing zone. So that is a great help for the fishermen. So these are the many applications which for the benefit of the people. And also this is one project I was talking about, drinking water mission. So we can predict that where the water we can predict that where the water groundwater is there. So now I will come back to the means work. So we are not application scientists. So this whatever we are doing, so that data is having this kind of applications. So what we do in NRSC is we receive the data from the satellite and track the satellite. So for LEO satellites, tracking is a very important part, because it's a big large reflector, so the gain is of the antenna is huge. So there is a very narrow beam, so there is margin of error is very less. So I will be talking about how to track the satellite and receiving data from the satellite. So we track with a reflector antenna. So you know that in reflector antenna, so it is basically a Cassegrain telescope or a prime focal. So same kind of thing is there. So reflector antennas means there is one type is prime focal feed. In that the feed will be located at the focus of a parabola. So there is a parabolic reflector, and we know parabolic reflector on focus is there. So in that the feed is located. So parallel rays will come and it will hit the reflector and it will concentrate in the feed. So this is one application, is parabolic, is prime focal feed. Then second one is now it can be offset also. This is used for basically TV antenna. This kind of configuration is used. So now for Cassegrain feed, it is a parabola and a hyperbola. So hyperbola having two focuses. So one focus we will place the feed and other focus will match with the focus of the parabola. So the parallel rays will come and hit the reflector, and after that it will come to the parabolic reflector, and from the parabolic reflector it will come to the feed. So the Gregorian obligation is same as Cassegrain, but instead of a hyperbola we use a ellipse. So it is an ellipsoid, this is an hyperboloid in the subreflector. So these are the 3-4 types that we use, but mostly we use Cassegrain because it has certain advantages. Prime focal is affected by the ground noise because the feed always looks at the ground, but the Cassegrain we look at the feed looks at the sky. So sky is more ground is brighter than sky, so noise is also more, but sky noise is less. That's why Cassegrain antenna receives lesser noise, and also we don't have to run a long cable, which is happens in the prime focal feed. So these are the main applications. So this is a animated picture of the tracking, satellite tracking. So we receive the satellite, we see the satellite at the horizon, then slowly it covers the total horizon, and antenna continuously track the satellite. So the satellite pass is about 14 minutes, and out of that there is data about 10 minutes or 7 minutes. So that imagery data is transmitted between this period. And now I will come to the satellite tracking. There are many methods are there. One method is program tracking method. Program tracking means we know that Kepler predicted three equations. In that he defined the trajectory. So with the mathematics, the satellite trajectory can be predicted. Means at what time and which elevation and azimuth satellite will be there, it can be predicted before. So and there is one file is made with that information, and antenna is fed with that file, that is called program tracking. That antenna is told to move along with the information in the file, and that is predicted from Keplerian equation. So this tracking is okay, but there is a problem that it is not very accurate. So in order to increase the accuracy, so there are different tracking methods, which from the initial days it is adopted. So one is method is lobe switching. Lobe switching means that one lobe will be rotated, and and the maximum return will be taken. And another method is conical scanning. Now in conical scanning, in lobe switching, what happens that antenna, the beam will be moved. So if you see the beam, if you see that from the A and B position, the return in B is more, so the target is located in the B, like that. It is a lobe switching. So it is a very crude way. So one more way is conical scanning. It is still being used in such areas. So in that the lobe is rotated continuously in a circular way, and we always get the return from it. So there is when the return is more, then the envelope will be more, and when the return is less, envelope will be less. So we got a amplitude modulated wave, on amplitude modulated signal, and that where we get more amplitude, the location is probabilities there. So these are the two things, conical scanning and lobe switching, but the most accurate is monopulse. I will be talking about monopulse only. So basic thing we will say monopulse tracking is adopted because it is very accurate, and it is free from mechanical vibration, and it has a high SNR. So now what is monopulse tracking? Now this slide is very interesting because it will tell that how the monopulse tracking is done. So mono, the word mono came, mono means single, one. So one pulse is transmitted, and from that we are acquiring angular information in both axes. So one axis is called azimuth axis and other axis is called elevation axis. Now suppose the satellite is in the center position, so at that time A, D, B, C will receive same amount of signal. Now suppose take the scenario when the satellite is slightly deviated and it is four antenna elements are there, and it is more it is little bit more close to A and D. So A and D will receive more signal and B and C will receive less. So if we add A and D and subtract it by B and C, so that will give the information how much it is deviated. That will give the information how much it is deviated to the elevation axis. Same way when satellite is deviated in the A towards A and B, that means in the azimuth direction, then A and B will receive more signal and D and C will receive less. We will add A and B and subtract it from D and C, and that will give you the azimuth information. So from the monopulse tracking we gather three information. One is sum, that will the intended signal that we receive from the satellite, and then angular information in azimuth direction and angular information in elevation direction. So these three signals are then processed, and now this will give another slide. So here it is shown as again 4 element. So 1, 2, 3, 4 are the 4 elements. Now you can see that from here sum is there and error is there, and from here also the sum and error is generated. Now these two sums are added and this will give the sum signal, and then again from these two A and B we will get A minus B, and then again from this also we will get the minus 3 and 4 we will get the minus. Then after that from these two we will get the azimuth, and if you subtract these two we will get the elevation. So this is the basics of monopulse technique. Now you can see that what is the design challenge. Main design challenge is that we have three patterns here. One is sum pattern, another is elevation pattern, and azimuth pattern. So in this case all three patterns have to be optimized. So this is the basic optimization goal, and also this slope is also important because it will determine the accuracy of the satellite, and also if it is very narrow, then we lose the satellite, we will have a very narrow loop angle. So these two things are there. One is slope should be more, and also narrow angle should be, this angle should be wide. So these two things, this is the loop angle and this is the slope, and also sum we have to get maximum sum signal. Maximum sum signal will maximize GYT, and means gain by noise temperature of the antenna. So gain if you maximize, then your GYT also increase, then you will contribute to the link margin. Then if you have a very good efficiency, then you can reduce the antenna antenna size of the onboard satellite, and that will add to the your cost of the system. So these are the basic challenges. So what are the feeds generally used? One is a 4 element feed. 4 element feed is very attractive, but because of the simplicity, but when we take the sum signal, then A, B, C, D all four has to be added. So all four have to be added, and because of that the addition we have to use a comparator circuit, and that will encounter some loss. So this 4 horn feed is not generally used, but it will give some loss. So one more feed is multi-mode feed. This is a very sophisticated feed, but it has It has a mode coupler, so it uses T21 mode coupler. So this is the fabrication constraint is there because that mode coupler, particularly at higher frequency band, will have a very tight tolerances. So this is for multi-mode feed, and then third one is a 5-horn feed. Now I will be talking about 5-element feed that we have used. Now 5-element feed is, it is very simple. Why there are 5 elements. So from that, main element is the center element shown here. So center element is a corrugated horn in our case, and these are the 4 waveguides. So these are the small elements, and this is the element we will take the sum signal from it. So now this is the 3D, this is the basic schematic diagram of a 5-horn feed. So here, as I told, that some signal is taken from the this big aperture, and error signal is taken from the other this aperture. So if we add a plus b, if you take a minus b, so that will give you elevation, and if you subtract c minus d, will give you azimuth. So this is the basic block diagram. So this is very interesting. This is very interesting. I will be explaining this. So this is the this is it stays at the heart of the monopulse single channel monopulse technique. So from here it is clear that A and B, if you pass it to the 180-degree hybrid, then add this delta sign, you will get elevation, and that is called A minus B. Again, C and D, if you pass through 180-degree hybrid, then you will get azimuth, that is C minus D. Now at this point, what you have? You have elevation and azimuth. Now, and also from this you get the sum signal, right? Now there is a switch here. So this switch actually basically a combiner of azimuth and elevation, and there is a delay line 0 degree and 180 degree. So suppose at T1, so it is the first switch is in the blue, and the second switch is in the black. So this switch is operated faster, twice faster than the second one. Okay, so at T1 we will get elevation 0. Now this will switch, as it is slower, it will remain at this position. It will remain at this position, but this switch will come to azimuth port. Now at time T2 we will get this path, that is azimuth 0. Now at the third instance, what will happen? Again this switch will move to elevation port, but this time this switch also moves to 180 degree line. So like that we will get elevation at time instance 3, we will get elevation 180 degree, and then at time instance 4 we will get azimuth 180 degree. So this switch will be here for 2 instances, so we will get azimuth 180 degree. Now what we got? We got elevation 0, azimuth 0, elevation 180, and azimuth 180. Now at time, now here we are with the 6 dB coupler, we are adding azimuth and elevation. So at time T1 what we get? We will get azimuth plus some. 0 degree means it will be added, and 180 degree means it will be subtracted. So we will get azimuth plus some plus azimuth, and some plus azimuth, and some plus elevation, then some minus azimuth, and some minus elevation. So if you plot this one, then this is the signal, this is the thing you will get in a real time scenario. So at here this is some plus azimuth. Okay, now at this point this is some, at this point it is some plus elevation, then after that it will be some plus azimuth and some minus elevation. So there will be 4-step signal will be created with this. Now, now I will come to the design of a 5-element feed. So the 5-element feed means the 5-element feed is a this feed is a dual polarized feed first of all. So we will use a corrugated horn as the main element and 4 circular septum polarizer as a tracking element. Now here the advantage is this will become very compact. Now dual polarization will be achieved through circular septum polarizer and also rectangular septum polarizer will be feed for the corrugated horn. Now why this corrugated horn is used? So in the corrugated horn part we will have T11 and if you use this conical horn, then it supports T11 mode. Now this T11 mode is the aperture field, we can see that it is not linear. Now if there is a linear, it is not linear, then what will happen? This X component which is creating this nonlinearity, and that will radiate in the other direction, so it will encounter in the cross pole, and also the beam symmetry will be less. If the beam symmetry and cross pole we have to match, then we have to make this aperture field as linear. So how we can meet linear? We can add higher order modes. Now if we know that in a waveguide, if you put a discontinuity, step discontinuity, then higher modes will be generated. Now how to add this? It will be add in a particular ratio, and then we will get a HE11 mode, and this HE11 mode is this is HE11 mode. Then you can see that these aperture fields are linear. So this is the corrugated horn. So corrugated horn, the main design parameters of the corrugated horn are this mode converter. Then in mode converters, one is a smooth section, so it will start with a smooth section, then there is a mode converter, and then after that the corrugation will be there. So this corrugation you can see it is more clear here. So this is the smooth section. So this smooth section will determine the return loss or the matching. Then after that we have a mode converter. This section is called mode converter. So mode converter section will generate that HE11 mode. Then after that this HE11 mode should travel to the aperture. So this slot depth are determined by these equations given, and with that we have generated this corrugated horn. Now this corrugated horn is simulated, and this is the RSCP and LHCP. Now one thing I want to tell, that these tracking waveguides or tracking horns, they are placed wide apart. Now if they are placed wide apart, then there will be grating lobes created. Now that may create a nonlinearity in the secondary pattern. So we don't want this. So to bring those tracking elements close to each other, we have done some perturbation. Perturbation is done in the in this horn, corrugated horn, so that in this cut this tracking elements will sit. So because of this, we don't think that we have simulated it, and we saw that there is not much change in the simulation. So this is K band. So this is the X band circular waveguide polarizer. So polarizer used this is side launch polarizer. So this polarizer is very interesting. This two you can see that in a circular polarized wave you can separate it in, or you can is a combination of two linear polarized wave. So this is a y axis and this is the x axis. Now when there is a septum which encounters a septum, then that modifies this vertical waves will be vertical polarization will be affected, and it will generate this kind of thing. So at the left part you can see that they are opposite of each other, so they will cancel each other, and at the right part it will be added. So for this, in the right part we will get RSCP. In the similar way, if the direction is opposite, we will if the direction is opposite, then we will get LHCP. Now this is the fabricated structure, and this is the simulated and measured return loss for this. Now this is installed in the system. This is simulated pattern and measured pattern. This is shown as the installed in the antenna. This figure is shown here. This is simulated secondary gain. So we got a efficiency of 83%, and the sum gain is 51 dB. The difference gain is 40 dB. The G by T measured as 29.5 dB. So I will now I will come to this my second work. How much time I have?
The talk is for 45 minutes, but you can take up to 1 hour.
Okay, means from now half an hour?
Yes, sir.
Okay. So now I will come to the second work, design of a dual band and dual polarized monopulse feed. So it is a composite feed. Now I told that we have to use antennas of same aperture and same antenna aperture we have to use for different frequencies. Now satellite will transmit the information not only in one frequency band, but it will transmit in a multiple frequency band. So for that it is required. So so design of this dual band feed, I will come to this. So this is a K band K and S band feed for 7.5 meter reflector. So K band feed, this actually the profile is known. So we have to design a feed for this optics. So this feed consists of K band feed, K band 5 horn monopulse feed, K band waveguide component, K band waveguide network, and then S band feed assembly, then a shaped reflector. Now this is a specification given for the design. So antenna is a 7.5 meter antenna, subreflector is 736 meter diameter. So we want to have a gain of 63 dBi for K band and 42 dBi for X band. And the error pattern is, we will have a null depth of 30 dB. So these are the design component of K band: corrugated horn, tracking elements, septum polarizer, magic T, waveguide bend transition, then waveguide bend transition, some circular to rectangular transition, and then S band components, S band dielectric rod elements, and S band polarizer. Now design of corrugated horn. Now corrugated horn design I have described earlier. So same kind of method will be used to design a corrugated horn. Here also perturbations are made. Here also perturbations are made. So now here we have tracking elements. Four circular tracking elements will be there. Now these are flare waveguides. So this array will give the primary pattern. This is the K band corrugated horn schematic diagram. Then after that we will have a different type of polarizer. This all polarizer internal design is same, but it is having different length. Now this is the magic T and band transition that are used. So all these together, put together, this up assembly and down assembly will be generated. So this is basically to extract the error azimuth and elevation error. So I will explain from this figure. The design can be explained from this figure. So you can say that see that there is a main horn, that is corrugated horn, and there are 4 waveguides. This waveguide is flare. So this is the main element and these are the 4 tracking elements. So after this, here there is a rectangular to circular to rectangular transition, and after that there is a polarizer. Now polarizer will separate RSCP and LSCP signal. Now this RSCP and LSCP signal, when they are separated, then they are given feed to the magic T. Now magic T with a brain transition. So the magic T will do A minus B. Now we need, for this circuit we need 2 magic T for one polarization and 2 magic T for the other polarization. So here we will get azimuth RSCP, and here we will get azimuth LSCP. Similar way, here we will get elevation RSCP and here we will get elevation LSCP. So this design is completed, and after that it is taken to the CATF facility, and in the CATF facility it is measured. Now this measured result with the compare with the simulated result, and we can see that it is a very good match, but in the in this region there is some deviation. So actually although there is some deviation is there, so the antenna, the feed will see only the up to 17 degree, that means subtended angle to the subreflector is 17 degree. So after that the energy is a spillover, so it will not affect our system. So up to 17 degree the pattern is fine, and also K band measurement inaccuracy is also present. So the measured gain is 21.2 dBi and simulated difference gain is peak gain is 10 dBi. So so this is a composite feed. So whatever I told, say this, if you take S band also, so here one thing, K band and S band feed are co-located, means they are located in the same Cassegrain plane. Now there a S band feed, for that there are, it is a array of 4 dielectrics arranged into 2 configuration. So and it is fed with a circular septum polarizer. Now this dielectric rod, again it supports the hybrid modes and it will generate a symmetrical beam, and it is fed with a circular septum polarizer, and from the here we can get RSCP and LSCP. So this makes the system very compact. So this is the 3D view, this is the top view, and this is the side view. Now this is the fabricated picture of this K band horn. This is a dielectric rod, and this is the this is 4 dielectric rods, and inside that this is K band corrugated horn, and this is the K band waveguide network, whatever I am showing, up assembly and down assembly. So K band waveguide network is here, and this is a picture, zoom picture of K band corrugated horn. This is a fabricated picture. It is gold plated, and you can see the corrugations inside. Now whatever we got, whatever we got the primary pattern, that pattern is feed to the in the software, in Tigra software we are using. So in that we have the profile of 7.5 meter reflector, and we have the measured pattern, measured S band and K band pattern. So these two patterns are fed in the software. We computed the secondary pattern, and secondary pattern is achieving whatever the desired specification. Now I will come to the dielectric rod. So this is the dielectric rod array. This is the dimensions of the dielectric rod. So gain achieved for a single dielectric rod is to 16 dBi, and when we get an array, then it is almost 21.14 dBi. The simulated pattern is 21.4 dBi, and we have measure pattern and simulated patterns are matched here, and they are showing very good match in terms of uh, difference and some pattern. Now again this pattern is simulated with the profile, and we got the desired gain here. This is the RSCP and this is the LSCP signal, and this array is arranged in this configuration. So this is the dielectric rod array. So this feed is a 4 element dielectric rod for S band. K band feed is again a 5 element feed, and then there is a waveguide network to extract azimuth and elevation error. This feed is fabricated, and I shown you the CATF tested results. This is indigenously developed and fabricated with in-house facility. Now I will come to the one more design, that is SX design. This is also a composite feed design, and this covers 7.8 to 8.5 gigahertz. And the required G by T for this is 32 dB, and the null depth is 40 dB. So this is again dual polarized simultaneous RSCP and LSCP for S band and X band. So this is the schematic of the corrugated horn. Again, there is a smooth section, then a mode converter. So smooth section matches return loss, I told you. Then again there is a mode converter. Mode converter will convert T11 to HE11 mode, will give gives a linear aperture field, and from that this will be propagated to the aperture, and this at the aperture we will get a very low cross polarization symmetric beam. So this is WR112 waveguide, which will be used in the feed. Then after that, these are the X band components. So this is the X band assembly. This clearly shows the X band assembly. So there is the main element, and after that there is the tracking element, and after the tracking element is feed with the circular septum polarizer, as I shown you. In the X band also we are using a different same type of circular septum polarizer. So the advantage of this circular septum polarizer is you don't need other waveguide junctions or waveguide component. Earlier what we had usually used is one uh, rectangular to coaxial adapter is being used, and one transition being used, waveguide transition. So all these components are removed, and directly we can get azimuth and elevation. Sorry, directly we can get a RSCP and LSCP output. Now this will be fed to 180 degree hybrid, as I told you in the earlier block diagram. If you remember that, with this will be fed to this you can say this is A element, this is B element. So output of this will be fed to 180 degree hybrid. This will give elevation, and again these two output of these two will be given one more 180 degree hybrid, and that will give azimuth output. Now this output I will combine for the monopulse tracking. So these are the fabricated structure of the septum polarizer. Now again this is also measured in the CATF facility, and you can see there is a excellent match between simulated and measured pattern for both sum and difference signal. So this is the 3D assembly of SS band, 3D SS band assembly. Inside there it is X band corrugated horn and 4 tracking element, flare waveguide, then circular septum polarizer, and this is S band. 4 dielectric rods are there. They are fed with a S band circular septum polarizer. This is the top view, and this is the side view. So this is the basic feed circuit. So I have already discussed this. This is the building block of a monopulse single channel monopulse technique. So after that, it is the fabricated structure of S band composite feed is shown in the figure. So these are the four dielectric rods, and inside there the K band, sorry, inside there X band corrugated horn and four tracking elements. And this feed is then after that we have generated the simulated primary pattern, simulated secondary pattern from the measure pattern we got. This is the corrugated horn picture. So this feed is installed in 7.5 meter reflector at Jodhpur, and this feed is now currently operational. It is tracking real time signals, and we have achieved a G by T of X band G by T 32 dB. Expected G by T, more than expected we got. This is a very good achievement. And after that we got a S band G by T of 16 dB with all the means at the receiver. So this is complete work. Actually this feed is now currently operational. Now after doing that, I will be these are the present work which is on progress. So this is it. I told you that different types of feed choice. So one more feed choice is T21 mode coupler. T21 means this is a T21 mode coupler. So T21 mode coupler, the advantage is from the single aperture we can generate azimuth and elevation. So here instead of multiple elements we use multi-mode, means T11 mode will be used for sum, and T21 modes gives a null at the center. In azimuth and elevation both we can get the null. So T21 mode will be used. So this is for x and carbon. So for that x and carbon, you can see that S band is a sorry. So S band is a S band dielectric rod, whatever I have shown you earlier. K band tracking elements are again circular septum polarizer, and this will be a corrugated horn or a Potter horn. One more application you can say that Potter horn also used for adding higher order modes, but corrugated horn anyway it is superior. And here from here with X band with a T tensile junction, T11 mode will be taken and it will be combined. This will give the error. There are four tracking elements will be there, so this will give the error, but sum will be taken from this. It will be combined again, then this will give the sum. And inside this X band element, one K band rod will be inserted, and this rod from here we will get T21 mode will be taken from here, and T21 mode will give the azimuth and elevation, and this is T11 mode. This is will be used as a sum signal. So this is the basic thing of a tri-band design. The design is in progress, and this is the schematic of that. This is the X band, this is the S band dielectric rods, and after that this is the waveguides for tracking elements. And after that this is tensile junction from where the X band is taken, and this is the T21 mode coupler for K band. So this is again I told you, this is the S band dielectric rods, this is the X band thing. So X band thing, and after that this is the from here we will get the sum, and from this tracking elements we will get the error. And this is the K band thing. So K band thing will be, this is a dielectric rod inserted inside the corrugated horn. Now and this is the K band mode coupler. Now one challenge is there, that when we matching is the main challenge here. So when it is a corrugated horn, then we don't have any design problem. When it is a dielectric rod, then also we have the design. But when this dielectric rod is inside the corrugated horn, then there is a huge matching problem, because now it is not a pure waveguide, but this is a TEM waveguide. Not it is now it will the first mode will be TEM mode. So here we have used some rings to get the matching. So this is the matching section, and a K band is not degraded that much, but X band return loss degraded after inserting this. So X band matching is obtained with this. So this is the total thing, you can say. S band is dielectric rods, then again corrugated horn, and this is the mode coupler design. This design is completed, and this is the mode coupler design. This is a very complex design from where we will get the azimuth and elevation error. Now, if I have time, I want to discuss something about the installation, because we not only design part, we also take care of the installation of the antennas, because from the initial stage installation of feed and installation of other subsystems, front end electronics, then down the line we have other monopoles electronics, then we have down converters, and then we give it to demodulators. So the total thing we take care. So we have several several antenna installed in different places in India. In NRSC we have 4 7.5 meter antenna, and then also we have some geostationary antenna, 3 are there. Then after that we have one 4.5 meter antenna. Then in other places, like for the defense application, we have installed many antennas. In DIPAC we have installed 2 antennas in Delhi, and in Palamkottai we have installed recently 2 antennas, and then in NTRO Dumduma we have installed 2 antennas. NTRO Delhi we have installed 2 antennas. So many 7.5 meter reflector antennas are installed for defense application, because nowadays satellite data is indispensable for the defense application, because because in border area you need a very close surveillance anyway. And also one more thing, very interesting one, we have installed antennas in Antarctica also. Now in the mainland, as I told that the visibility of the satellite pass is 14 minutes, and we get 4 passes in a day, 2 in the morning and 2 at the night. So there is a less visibility if you want to, but the satellite can take dump the huge amount of data if the more visibility is there. So in Antarctica we get the advantage, because as we approaches close to the pole, then the visibility of the satellite increases, and uh, we can see more satellite passes of in a single day. We have 11 to 14 satellite pass we can is visible, where we have installed at the antenna we have installed at the Bharti at Antarctica. There is a station, Indian station at Bharti. India has 2 stations, one is Bharti and Maitri. So in Bharti we are using we have used 2 ground station antenna. One was installed in 2012, and recently we have installed the second one. First one was installed, that is SX antenna, and the recent one is SX and carbon antenna. So whatever I told, that is also written here, that increase the visibility, and so as the visibility will increase, we can see more satellite passes, and more data can be dumped. So one more thing, that when this data is dumped in the Antarctica, then the question comes that how you transmit the data to our station, or in NRSC Sadnagar, then how the data is transmitted back to NRSC. Now all the data which is dumped at the ground station, LEO from the LEO satellites, that data is given to one more antenna, and that is looking at the geostationary antenna. So that geostationary antenna having footprint in Antarctica and also having footprint in Hyderabad. So that data is transmitted to the geostationary antenna, and it is relayed back to Hyderabad. Now earlier this is the link actually. So LEO satellite, from the LEO satellite, data is dumped in DRS1 and DRS2, data reception system 1 and 2. This is SXK and this is SK. So from here it is given to one more antenna, that is that is geostationary antenna. It is looking at GSAT 17. So this data is transmitted to GSAT 17 and it is relayed back to NRSC Sadnagar. So this is a low speed line, this is a high speed line. So data is relayed back to NRSC Hyderabad. So this is the block diagram, you can say, or it clearly explains the what is the purpose. Now earlier what happened, we used to use, instead of GSAT 17, we used to use one foreign satellite, Intelsat 33. So after in our expedition we have changed all the subsystems of the antenna, and all the subsystems are which are means matched to GSAT 17, that feed and SSPA, everything is replaced and it is made capable of transmitting to GSAT 17. So this is the installation team, and you can see the installation at NRSC. Now one more thing I want to tell, that in future one more interesting topic, interesting thing, because many research personalities are there. So one more thing is also coming up, that is instead of transmitting it back to a ground station in Antarctica, why cannot we transmit it to the from LEO satellite itself, we can transmit it to geostationary satellite and it can be relayed back. So ground station cost can be avoided in a remote place. So that is one more application that we are also looking for. Now with this I will end my presentation. If any question is there, you can, I am looking for that. These are some photos of Antarctica. Thank you very much.
Hello, sir.
Yeah.
Can you hear me?
As I said that I will interact at last.
Okay, sir.
I did not want to take any time. Sandeep, congratulations for the excellent talk.
Thank you. Thank
for
you.
Audience, yeah, our audience interest. Before the chat session starts, I just want to mention it's altogether a different ball game to have this kind of antennas. I mean, it's just antennas. It requires many other subsystems, as you have seen, those mode coupler, and you are receiving the data from the to the sum, and then the difference, the tracking, and it requires the servo system and control system. So all together, when you see, it's a very involved and a real, I won't say the term complicated, but it's a quite challenging job. And because of Sandeep's affiliation with ISRO, and of course they have a very good team, this work has been possible, and more are in pipeline, as Sandeep has mentioned. You will see. So you can control the chat box, Wilson first, Edwin, and then for benefits, I will say a few more at the end.
I will have some questions related to the
take those
talk.
first.
Yes, sir. So the first question is, how much antenna gain is required for tracking LEO satellite in terms of decibel in Monopulse tracking system?
Antenna gain, again it depends on the satellite EIRP. So it is a total link margin. So when in the antenna gains are different for different frequency bands. So at the receiver, no, this will be determined by your tracking receiver sensitivity. So if your tracking receiver sensitivity, it is in the order of minus 50 dBm. So with that, so minus 50 dB hertz is the minus 50 dB hertz is the that is the C by N naught. We get that is the limitation. So if your tracking receiver is more sensitive, then the gain requirement for tracking is less. Again, for data chain, it is dependent on the BER, means bit error rate of your receiver, means how much bit error rate if you want to get. So if you want to get a 10 to the power minus 6 order of bit error rate, then for X band the antenna gain is 54. For S band it is 42, and for K band it is 64 dBi. Hello. Hello.
Yes, sir.
Yeah.
So the next question is, the sum and difference pattern antennas can be used in DRSC band 5.9 gigahertz vehicular applications.
Yeah, in that if you are able to generate sum and difference pattern, then it is possible for that band also. But means for a moving object, certain things you have to be taken care. Like I didn't understand that, and for which application, means for moving vehicle you are telling.
So the question is, sum and difference pattern antennas can be used in DRSC band. In within brackets, it's written 5.9 gigahertz vehicular application.
Yeah, sum and difference pattern anyway it can be generated in vehicular applications also, but there I don't think that reflector antennas will be used. So in microstrip also you can generate a sum and difference pattern.
Okay, sir. The next question is, why are we using conical horn instead of pyramidal horn?
Basically, for circular polarization purpose, we are using conical horn. So circular polarized needs a symmetrical aperture. So square horn can be used, but conical circular horn gives a better performance than the square horn.
Let me interject here a little bit for the audience who are asking these questions, like considering that most of them are youngsters. So to understand and grasp this idea in a better way, first you read the basics of the horn antenna, right? If you go to the basics of the horn antenna, and those who are aware of the fact and the history, then you will see that horn antenna, which initially some people used to call as funnel, that was the initial contributor for millimeter wave band was none other than Jagadish Chandra Bose, right?
Yes, sir.
The history. And then if you see the corrugated horn and different kind of modification on the structure that happened, has been mainly contributed. And with him, the person who worked was our professor, Professor Pradip Kumar Saha. Okay, so the corrugated horn, the development from pyramidal to conical, then complicated structure, corrugation, and all these things, you will get this idea from those classical papers, IEEE, some of the papers in IEEE microwave theory and techniques, because Professor Saha, my professor, I am also Saha, Professor Pradip Kumar Saha was a robust mathematician and robust electromagnetic engineer. So you have to start from that area to understand the basic thing properly, to grasp the full knowledge of this thing. So someone was asking for the PPT, so I am advising. So don't, if you won't get that much benefited, even if you get the PPT. Moreover, there are classified material. So better you don't ask or expect this kind of thing. So the advice is you go and read the basics of the work by Professor Claricot and Professor Shah. Okay, yeah.
Thank you, sir. The next question is 51 dB gain achieved from a single antenna or from antenna array?
No, it is from single antenna. Means basically there is a feed, and the feed is illuminating the subreflector, and eventually subreflector is illuminating the parabolic reflector. So like that we are getting the gain. So it is not from an array.
Okay, sir. I hope the doubt is. I hope the doubt is clear. The person who asked it. So going on to the next question: will increasing number of horns around the corrugated horn give a better precision for tracking? Will that cause interference?
Actually, we increasing more horn will not give the ultimate result, because we need 4 horns, and from that now aperture, the question, very good question will be the whether we can increase the aperture of the difference horn or not. Now if you, there is a trade off, if you increase the aperture, then the inter element spacing will also increase, so that will generate the grating lobe. So this is a compromise been made to reduce the grating lobes and also keep the difference gain in a considerable amount, or the required amount.
Okay, sir. Thank you, sir, for clearing the doubt. Moving on to the next question: how corrugated section act as a mode converter?
Can you come again?
How corrugated section act as a mode converter?
Okay, corrugated section is not a mode converter. Corrugated section is to from T11 wave, T11 mode to hybrid mode. It is generating HE11 mode. That is the work of corrugated section. Mode then okay, mode converter. It is a mode converter. Yes, actually, what is happening when you give a discontinuity in a waveguide structure, then what happens? Higher order modes generated. Now when you have a periodic discontinuity, then what happens? The higher order modes that are generated also will be attenuated, and the required mode will be added with the fundamental T11 mode. So here T11 mode is added with the next higher order mode, and that is giving that is producing a linear aperture field. So this is the answer, I think.
Thank you, sir. So next question is
one more thing, Shapnil.
Yes, sir.
So the paper I was talking about by Professor Shah and Professor Claricot, I have posted that in chat box. So for all the participants, this would be greatly beneficial. So because you are asking some questions, sometimes I feel like for the sake of asking. So you need to understand the basic. We go back to the very basic things, because what Sandeep is presenting is probably the output of some 10 years work. So without knowing the basics, you won't grasp the full idea. I suggest all the youngsters to read these basic papers first. Professor Claricot and Professor Shah. And there are many others, of course. So somewhere you have to start. So this is a very good starting point.
Thank you very much, sir, for sharing the link of the paper. We all youngsters will look into the sheet. And so moving on to the next question, it is what is the power level? Not that much clear. This is the question. What is the power level?
So the thing is, we have the application we have described here. It is for ground station application. So for receiving antenna, power level, I think it is insignificant, because we receive a very less power from the satellite. Anyway, as it is for a corrugated horn, it is a pure metal structure, so power level will be very high. And also we do for dielectric rod and microstrip components, the power level will be a concern. So we transmit, we do transmission for S band, and in that we transmit in the order of 100 kilowatt.
Okay, sir. I guess that's all with the questions.
Excuse me. One more question you left. Kindly inform where the fabrications have been carried out.
Professor Raghavan, good evening.
Yes, good evening, sir. It's a wonderful lecture.
Sorry, sir, I forgot.
When you've been talking about planar transmission lines, for a change, wonderful lecture, discontinuity, everything in waveguide. It's a classic lecture. I am very much.
Why don't you turn on your video? We want to see you also. Yeah, Sandeep, you may give some ideas regarding the fabrication unit and all, the measurement also.
So I would like to know where the fabrication has been done.
Yeah, good evening, sir. Thank you for your comments. So this fabrication is done in Hyderabad. So we have in-house facilities, and also we have collaboration with one small company, that is Silicon CNC, and also we have collaboration with ECIL, Electronics Corporation of India Limited. So they have done the fabrication, and it is tested in CATF facility. ECIL have very excellent CATF facility is there in ECIL. There you can up to 2.4 meter reflector antenna, you can measure it with that CATF facility. So with that fabrication and measurement is done there.
Okay, sir.
That is one of the wonderful facilities for the chamber measurement, that anechoic chamber. And that anechoic chamber, as you know, is a big one, and you can test with a large quiet zone, and therefore you can test this kind of antennas, which normally Sandeep is a real practical engineer come scientist, so he himself measured the pattern of most of these antennas.
The way in which he delivered, I can even coin him is the Markowitz of India. All the waveguide components, including step discontinuity, unimaginable. That's why I was thinking whether the fabrication also done in India. And this comment is not only from me. Most of the participants have expressed admiration of waveguide components. Practical lecture. Wonderful, sir.
Correct, sir.
Thank you very much.
Correct. I join with Professor Raghavan in congratulating him.
Good evening.
Good evening. Because the thing is that we have been teaching this tracking and all monopoles, but we read from Skolnick and teach. But it is very interesting to
sorry.
from a
Professor
person.
I thought it is Sammuganathan.
So, through Dr. Chinmaya Saha, stalwart Anandan, K. Anandan also is here. So very rarely we get the lecture on waveguides.
The video, not the name panel. I just anticipated from the voice.
Yeah. So it was really interesting to hear it from a person who is doing it, practically doing that one, instead of because that is the difference between an engineer who is doing that. So congratulations.
Very nice comment from the ex-president, chairman of APS Kerala.
Yeah.
Thank you.
One more thing.
Thank you very much, sir.
Sandeep was shy to tell about the Antarctica installation part. So we remember a phase where both of us used to talk, and over WhatsApp probably. And the first few lines or first few minutes of the talk is how much is the snow and what is the temperature. He's asking me, I am also asking him. Because he was around minus 30 degrees at that time.
One more question.
Around minus 30, minus 40.
Is he working in ISRO or NRSC?
Sir, now ISRO is a part. NRSC is a part of ISRO.
Okay, okay.
Yes. NRSC is part of DOS and part of ISR.
I know one candidate who did research in NRSA, Dr. V.R. Anita.
Okay.
Okay, so
Thank you.
you can take the lead
Yes,
and
sir. Yes, sir.
do the rest of the proceedings.
Yes, sir.
Okay.
Yes, sir.
That was a.
So I guess.
Okay. I will take the lead. Okay. So this has been a really informative and a really practical presentation. So I guess we have all studied these theories in our class, and this was a good opportunity to learn from the person who actually did all these things. So that was a really wonderful opportunity, sir. So thank you, sir, Sandeep sir, for providing us with this wonderful lecture. I thank you on behalf of IEEE APS Kerala section chapter. So now we have come to the end of all the sessions of this conclave, and now we are moving on to the closing ceremony. So this has been the first edition of All Kerala APS Students Conclave. And this was an idea that came in our heads. So to be honest, there wasn't much student branches in APS Kerala section 2 years back. It all happened in these 2 years, and we decided to go on with this conclave. So it will provide an opportunity for collaboration between all the APS student members in Kerala. And I'm very happy that we had good participation from all of them. And from the first day, we had Dr. Yahya M. Andar sir, the IEEE APS president-elect, who came and inaugurated the event. And and we also had the presence of Dr. Javed Y. Siddiqui, the Region 10 APS IEEE APS chapter head. And along with that, we also had all the former chairs, starting from Dr. P. Mohanan, Dr. Anandan sir, Chinmoy Saha sir, and Abdullah sir, all who graced the event. And after the inaugural ceremony, we had the first talk, which was on ST radars, and it was ST radar at Cochin. So this is the first ST radar in the world which works in 205 megahertz, and it was a very informative talk. So Dr. Mohanan sir gave the talk, and it was really exceptional. And the second day, we had a panel session. Sir, fortunate enough to get the presence we have of Dr. Yakia Andar sir during the talk, and it was also graced by the presence of Dr. Javed sir, Dr. S. Ghosh, and Dr. Devdeep Sarkar sir. So that was also a very informative and productive session. So I thank all of them for coming and joining us in this conference. Second session itself, and today we have a talk by Dr. N. Nasimudin from Singapore. He talked about energy harvesting antennas, and now we had a talk by Dr. Sandeep Sankar Roy from NRSC on satellite antennas. So it was a pretty informative 3 days, and I'm very thankful for all the dignitaries who participated and all the presenters who gave us this information, wealth of information. So I am thanking you all on behalf of IEEE APS Kerala section chapter and IEEE APS Kerala section branch chapter. So thank you all. And now I would like to welcome the former chairs who are present here. I will welcome, first I will welcome Anandan sir. Anandan sir, are you here? Hello. I think he not there. So I will ask to give a feedback how on the experience of this conclave.
Professor Anandan is there. Professor Anandan, please unmute.
Anandan, sir.
Getting muted and unmuted. Yeah.
I had to change my net. There is some problem. I had to change my net. Hello.
Hello, sir.
Disable the
Yes, sir.
Yeah, or I will.
We can hear you, sir.
Okay. So we have just concluded 3 days of vibrant activity. So we could see many of our researchers and students who have attended this program. I wish to congratulate the students for arranging this excellent program. Very happy to see that there are many students interested in this area. Of course, I missed yesterday's program because of I thought it was at 7 o'clock. So sorry for that. I couldn't attend yesterday's program. So we have listened to eminent speakers. They have talked on very relevant topics. So we should the student chapter, they have to arrange more programs. So the enthusiasm which you have shown in these 3 days should continue. And you should have a variety of programs like say a design contest and something like a virtual visit to industry, because in this current situation we are not able to visit industry, at least a virtual visit. Because just now concluded talk, we have seen many things which are done in ISRO, but they may not be able to show it in real time. But there are industries which are manufacturing this type of things. If we can have some people from industry who can show their visit facilities real time along with the talk, it may be much beneficial for the students. So this student conclave was possible because we have many chapters, student chapters around Kerala. And I wish to congratulate Dr. Chinmay Saha in this because he has done excellent work in creating many chapters in this. I should once again congratulate him for that because he has done, I think, in Palakkad and in IASB and also in Barton Hill we have, and then now in Kusat we have the chapter, student chapter. And apart from arranging the programs, I think it is equally important to report these things in a website. You are familiar with the tools. You should do it in a proper way. You have to, do the reporting. So it is mandatory, but many times it is seen that we are not doing it in a proper way. And I experienced this in 2018 when we got that chapter award for the activities in 2017, and we have to make the what you call the application for outstanding award before March 31st, and we should do the all those things. And of course, as Edwin pointed out, there were no aptitude to volunteer for this, but now the situation is changed. So we had many programs during that time. One more thing is that we should have programs spread all over. Now we have webinars, but it can be attended by all, but still you should involve the people from all other engineering colleges who will be interested in arranging this type of programs. So nowadays it will be easy. Even though they don't have that chapter, student chapter of APS, there will be SB. You have to involve them also in arranging this type of program. Not only for getting an award or something, but increase your visibility and that connectivity which IEEE is for. That we have to of that one. So that's what I want to say. We will be waiting for many more things to come, and I thank you for giving me this opportunity to opportunity to be part of this program, and we are waiting for many programs to come. So wish you all the best for all chapters. I congratulate all the student chapter chairs who has done excellent work in conducting this program. Thank you.
Thank you, sir, for your excellent words. It is really inspirational. So as you said, we are actually by conducting this event, we have had some ideas come up. So I'm sure all the SP chapters will continue with the activities continuing in this year. The All Kerala APSSC, I think it is mentioned to be an annual event. So every event we will have vibrant APS student members will join together. So right now, because of Corona or because of COVID-19, we are doing it in virtually. But from next year onwards, hopefully by then the world will come to a normal condition, and then we plan on conducting this event, this AKAPSSC event in a cycle in different student branches. So right now we have 5 student branches. So so each student branch will host in a particular year. So in that way, so I think that will help bring the students into the society. So thank you, sir, for your kind words. Now I invite Dr. Chinmoy sir to give the final parting address to the conclave.
Yeah, thank you, Edwin. And as I told, this is by the students and for the students, right? So you have conceived the idea, the name All Kerala. It is All Kerala, but it is All India also. In the sense, I see a lot of participants from different corner of India. When this webinar activity started around April or probably May, we did the first webinar in this particular area by a young guy. So at that time, there was huge response. I used to see almost more than 200, 300 participants. But gradually, what happened was, like cricket in India, every here and there, people started doing webinars. I have discussed this with some of my senior colleagues also, and we named them as a webinar fatigue. So due to this webinar fatigue, the audience and the enthusiasm started decaying also, in the sense, without seeing the dates of the other organizers, without seeing the focus, without seeing the speakers and everything. So people were just organizing for the sake of organizing. So that's what we meant webinar fatigue. And now I see in many of the events the participation is really less. But in this particular APSSC, we have seen on the day 1 and day 2 and today also at the very peak again, we have quite good participation. So at some point, I remember you had more than 130 participants. So that was really good. And getting president-elect on 2 consecutive days, senior veteran and very busy person like Professor Yahya Antar is probably very unique. And I know many of the other student chapters across the globe will be very, very envious to you, right? So it is indeed a great achievement. Everything went very well. Starting from the first talk by Professor Mohan, there was a glitch during Professor Antar's inaugural talk on that day, but very nicely, you know, compensated on the second day by his full presence for the whole day, and he very nicely illuminated the panel. I was also part of, so I don't want to praise that, but other panel members were really good, and all the questions which you took a priori through the submission of Google form and also the online questions or the chat box questions were very nicely addressed. Today's talk by Nasimudin, I was not there for fully, but I know his work also because recently we had this Indo-Canadian workshop at NIT Shilchar. We talked on similar kind of topic there, and I also was one of the speakers along with the Yahya. So that talk must have been very good. And Sandeep's talk today, it was indeed a great job. And Sandeep is a young researcher, rather I would say mid-career researcher, and he can in fact create a lot of opportunities. That is something that, sorry, I want to see. That you people get benefited technically also. You are organizing very good leadership that enhances your administrative skills, managerial skill. At the same time, I want all the young UG students and some of the PG students to get technically affiliated and to reap the fruits of this particular workshop by technical means. What I mean by technical beneficial is you do real good work in these areas of antennas, propagation, microwave circuits, or wireless transfer or energy harvesting, or antennas for tracking applications and all. And then this, IEEE membership and antenna propagation membership and attending these webinars will be really more meaningful, because at the end of the day, when you complete your career, we want you to see enriched academically. So either you get a job as an engineer, or you go for higher studies with a good knowledge, good background, solid background. As we were mentioning yesterday, whatever research you do, the understanding of the basics is the basic requirement. So foundation or the basic is the most important. For example, the stuff Sandeep was talking about, if you don't know the waveguide modes, the T10 mode, the Maxwell's equation derivation, so those are the basic, and from that this is built on. Yesterday also I mentioned, sorry, that science clears the field on which the technology is built. Science clears the field on which the technology is built. So science means, what I mean is the fundamental, the basic. Physics remains the same. The technology changes depending on the requirement and all. So this is my advice to all of you. Sometimes you are getting overwhelmed by seeing some of the structures, some of the presentations, some of the applications, satellite and all, and the energy harvesting, and then Professor Mohanan's talk also, that ST radar. It looks really, very impressive, but you have to understand how much hard work, how much dedication, how much study has been involved in coming to that. And when you go back to the basics, it doesn't look that rosy. Sometimes it will involve a lot of calculation, mathematics, a lot of trial and error. Also, sometimes you will do some mistakes. So this is the point that I want to emphasize. Once again, a congratulations for this wonderful initiative. And as I suggested, that this should be a series, it should not be a standalone. And in future version, because of the COVID pandemic, especially in India, it's not going soon. So you keep it in a hybrid mode for next couple of years or so, and then you try to come up it as a hallmark of APS Kerala. That will be the real achievement from all of you. So and all, as I also mentioned, technical focus, you get benefited from these activities and from this rapport and networking, and then as I was mentioning yesterday, we can also, extend some other kind of initiatives like internship, and the project guidance also, because many of you are in some colleges, you might have a desire to do some kind of work, you might not have the proper facilities or proper guidance also sometime. So feel free to write to us, the senior people, Professor Mohanan, Professor Anandan, Professor Abdullah. I am also there with you. And these youngsters have been informed, like Dr. Shandeep, Dr. Sandeep, Dr. Saptoshi, all of them are really, asset to our country. And I'm pretty sure the earlier generations that we have seen, like the contribution from Professor Garg, and then Professor Kaul, of course, Professor Shivgaokwar, Professor Raghavan, Professor Mohanan, Professor Anandan, all are present over here. And then it is really heartening to see the youngsters, young generation, mid generations of the legacy of RF and microwave and antenna field from India. It still remains there. As mentioned by the president himself yesterday, that India, caters to the 10% of antenna propagation society membership. I just want to add that India has also contributed immensely from the technical fronts as far as the AP and entity society is concerned. That's why I intentionally mentioned the name of J.C. Ghosh during Sandeep's talk, and Professor Shah's involvement, Professor B.K. Shah's involvement in designing some of the most advanced horn antennas, which are the basic requirement for modern day satellite communication and many other applications. So I just want to conclude with this. You have done a wonderful job. Congratulations to all of you. Keep the momentum up, because you have already have a very nice launch. Once you have a launch, the next step is to get stabilized and to receive and transmit in a proper manner. So that is one thing is receiving, we are receiving the knowledge, and then I want to see the transmission. Transmission means this knowledge should be transferred in terms of tangible output. So I want to see you, all of you doing good work and coming up with some kind of publications also. So with this, I conclude again with congratulations to all the 5 student branch chapter chairs, because they are the pillars. It is their program. So all the best. Thank you very much for your all future endeavors. We are there always with you. That's it. Thank you.
Thank you, sir. Those were really kind words. And it was due to Chinmoy sir's effort that we were able to hold the panel session, and he brought Yahya Amanda sir. So we are indebted to your involvement in this conclave. So thank you, sir, Chinmoy sir. And
if Bridget, Dr. Abdullah is there, please request them to say something, because also Dr. Shukamol, the vice chair, Dr. Dipti, they are Dr. Kishore also,
so,
from Palakkad. Yeah. Sorry.
So right now we have our faculty advisor from Ahalya IEEE APS chapter, Kishore sir. Can you hear me?
Hello, Edwin.
Yes, sir.
I hope you can hear me.
Yes, sir. We can hear you clear. So I was hoping if you could say a few words on this conclave, on this initiative that you have taken.
Sure, yes. Good evening, everyone. So it's nice to see Chinmoy sir and Raghav sir and Anandan sir as well. I think it has been a wonderful event. It has been it's not as intensive as a usual conference where you have lots of talks going on, and you get confused at the end what happened in which talk, right? So it's not like that. So you had because it's webinar, in one way it's nice, you had limited talks, but I think the variety of topics that was covered was quite good. And so I hope you got a lot of learning experience and knowledge sharing, and I think like Professor Chinmoy said, you got to see or hear from people at least from all parts of the world, or at least from India at least. Now, with regards to the conclave, I think it's it's a great leadership experience for students. you'll get, it's when it comes down to the hard part, how to do a marketing of an event, especially on such a large scale, organizing speakers, scheduling talks, things like that. That's the nitty gritty part, right? So I hope you got all the chapter chairs who are involved in this. I hope that was a wonderful experience, and I'm sure it will be helpful for you in future as well. Um, finally, when it comes down to the hard part, you need to do all this. Someone needs to do this, right? So I'm glad the chapter chairs took this opportunity. Now, regarding for the so the PG students, maybe the masters or the PhD students, I hope you got a lot of starting points, for your research work. Good got ideas. That's the point of all these sessions. You may not be using the exact same thing what you heard, but when you hear from different people, you'll get a lot of ideas, and it saves time from reading that paper as well, right? Reading the paper might take a lot of time, right? But when you get to hear that person out, you can think on the spot, and if there are questions, you can immediately get cleared out. And there are no silly questions. All questions are equally good, right? So that's for the PG students. So I hope so make sure you note, you remember some of these points, maybe in your research you're using it, and even if not now, when you pass out and maybe you go into the academic field, you have certain points to start off your research, right? Now for the UG students, it's not, their numbers may be lower, but I hope the students who attended these sessions, get interested in the field of electromagnetics and antennas in general, right? It's a very underrated field. People talk about a lot of things, but they don't rate the antennas and the microwave field as high, right? So I hope there are a lot of UG students who get into continue their education in the masters, in this area of electromagnetics. For them, I hope it is a very good exposure to hear a lot of people speak, and how things are dealt with technically, right? So it's not expected that you understand everything in the first go, right? But as you take time to read about things, you understand and you appreciate the creativity that has gone in designing these various things, right? So it'll take time to sink in, but I hope the UG students get motivated enough to join this field. So yeah, so I think that's all I had. I wish all the students the very best. And it was a great experience, and I thank you for inviting me for this conclave as well. And I wish you all the very best. Thank you.
Thank you. So thank you for it. Is very inspiring, and all these words, it will help us to conduct more events in the future. And now I would like to invite a special guest we have here, Dr. S. Raghavan, sir. He's a senior IEEE member, and we would like to hear some few words from you, sir.
Okay, this is not a conclave. Dr. Chitmaya and all other student members have made it as an international conference. It is only because of COVID, all big people joined together at one place. And amongst stalwarts, Dr. C.K. Anandan, Dr. Chinmaya Saha, Dr. Abdullah, and also Dr. Anu Muhammad, there are 4 pillars. Because of them only, this is going to shine. And those pillars I don't need to mention. They are nobody other than Mitra, Sivada, Edwin Wilson, Ushmala. Maybe I would have missed some more students. So these are the people who made this international conference reach across the world, I can say. So as young stalwart Dr. Chinmaya Saga has told, let it come as an annual festival. Let it be as colorful as your Onam. Thank you all.
Thank you, sir. Those are really good. And let me take this opportunity now to welcome the brains behind this conclave. IEEE AP student branch chapter chairs. So I will introduce them first. So from Barton Hill, we have Swapnil Sinha. From IAST, we have Elizabeth. From Musaliar College, we have Subhana. From College, we have Ushmala. And from KUSAT, it's me, Edwin. And I would like to invite all the chapter chairs to tell a few words on their experience on conducting this event and also about the vision to the future. So
I apologize that I missed to mention these chats name. That's what I told persons behind the screen. Thanks a lot.
Yes.
Yeah. With video on and very brief because it is 10 o'clock now, right?
Okay, sir.
Yes, Swapnil, you can start. It will be a short speech. Yes, sir.
Thank you, sir. Everyone, good evening. So this is Swapnil, APS Chair, Government Engineering College, Barton Hill.
Turn on your video.
Sir, video is
it's on, sir. It's on.
Okay. As I said, I am APS Chair of JC Barton Hill. So I still remember after that APS Chairs meeting, we all came together planning and discussing to that we have to conduct an all Kerala APS. All the APS chapters in Kerala together to conduct an event. So we all 5 chairs came together and discussed and came up with this idea for a student conclave to conduct this. So unfortunately, due to the COVID-19, we did it as an online event, but it turned out to be a very successful event. I would like to thank Chinmaya Saha sir, who brought the stalwarts from the field of antenna, and his support and his guidance was immensely important for this event. And I'd also like to thank my college advisor, Professor Anu Mohammed sir. He was also a constant support throughout this event. And at last, I would like to thank my fellow chairmates from PUSAT, Ahilya, IIST, and Musliar College. They've been there. They have always been a constant support and cooperated. There was no issues of because since I am a BTech student and from the IIST chair is a PhD student and PUSAT there is an MTech student. So there was no clash between us. So I like how the things worked out between every one of us. Since we three were the youngest in the group, everything worked out very well, and it was a successful event. And I'm very happy. And thank you all.
Thank you. That was really wonderful. Now I would like to invite the PhD scholar from IIST, Elizabeth George, to give her thoughts on the event. Hello, Elizabeth. Hello.
Your mic is muted.
It's what
mic mute ആണ്. എലിസബത്ത് ചേച്ചി ഹലോ
I think we should proceed with the next year. She will come and
yes, I think she will reconnect.
We should ask someone else in between. She can fix it up.
Yes. So call upon Ahalya College of Engineering. Ushmala, you can come on video and share your thoughts.
I'm IEEE APS chair at Ahalya School of Engineering and Technology. I'm really very happy to be a part of this wonderful event. First of all, I would like to thank all the former APS chair who support us for this great event. I heartily thank Dr. Abdullah sir, all APS chair, and thank all the APS advisor who the also want to heartily appreciate all my colleagues for the restless duty and responsibility to run this event smoother. These periods journey a wonderful inspiration to all of us. I hope we can do more events for in the upcoming days. Thank you all.
Thank you, Ushmala. And next we have, I call upon Subhana, the APS chair from Musaliar College. Subhana, can you hear us?
Yes, I'm here.
Yes, Subhana, you can proceed. You can give your thoughts on the experience that you got from conducting this event.
Good evening, everyone. I'm Subhana, APS student branch here from Muslia College. It's a great honor to say a few words in this occasion representing my college. I'm feeling glad to be a part of this event. The success behind this event is the hard work and heavy efforts by most of the people here, and also the great coordination of this team. It was a great experience working with the people here for the recent days. Also, I convey my sincere thanks to Abdullah sir and Chinmay Saha sir for their great support. I'm looking forward to be a part of events like this in future. Thank you.
Thank you, Subhana. So it seems like Elizabeth has rejoined. Elizabeth, can you hear us?
Yes, I can hear you, but are you able to hear me? Okay.
Yes, you're audible now.
Okay, thank you, Edwin. Yeah, I say it was a very engaging and also very fascinating 3 days.
I think you can stop the camera because there may be some bad problem.
Okay, sir.
Camera?
Yeah, I've stopped.
Lagging.
Yeah, I have stopped the cameras.
Okay.
Yeah, organizing this AKAPSSC was a very challenging task when we started discussing about this among ourselves. Ushmala, Swapnil, Shibana, Edwin, and myself regularly had virtual meetings since the very beginning of August, and this required a great preparation and supports from every corners. And we got a lot of support from all our faculty advisors, Chinmay sir, Anu sir, Kishore sir, Deepthi ma'am, and Asim sir, and also our present IEEE APS Kerala section chair, Dr. Abdullah, and all our well-wishers. Yeah, and whenever we struggled in many things, everyone was there with us. And all of you might have seen only we 5 organizers who represent different colleges for the past few days. But I should say that there was an APS student community from each college helping us in all activities, from designing posters, drafting, sending mails, and all other activities. And we also started this event with a vision to unite the students at different colleges, not only on organizing conclaves, but also sharing information of various opportunities, and also to be like a helping hand when in need. So when we organize next year's All Kerala APS Students Conclave, I believe other colleges will also join us in the IEEE APS family and join with us in organizing the next edition of All Kerala APS Students Conclave. And I also would like to express my appreciation to all the participants, and I hope all of you enjoyed. Thank you.
Thank you, Elizabeth. That was really wonderful. And to give my experience on tracking this event. So when I joined MTech in Cochin University of Science and Technology, in my knowledge, there were 2 places in Kerala which offered MTech, and that was one was in University and was in CET. So say that the microwave and antenna field is really niche. And when I came to know that APS had this much members and experts in Kerala, and also the some branches overjoyed, because that means we have more people to collaborate, more. Yes, sir.
Can you just turn off the video? Your voice is getting cut off.
Can you hear me now?
Yeah, we can hear you.
Yeah.
Yes.
So I was saying, when I learned about the IEEE chapter in Kerala, and how I first heard about the stalwart section. So like Dr. C.K. Anandan and Dr. Mohan, all these people actually inspired me to really dive into the research of this antenna field. And now it was my aim to people know, to let other people into the fold of this field, because as we know, we can call antennas as one of the most crucial technologies that is propping up the world right now. Without antennas, we won't have this. We can't have this meeting. We can't have a connected world. So it is one of the clues that holds the world together. And we need more great minds. We need more collaboration. And this conclave I see as a step in that direction. So I am very glad to be part of this conclave, and I am very glad to collaborate with all the people, all my seniors, all my professors, all the senior APS members, my peers in APS. So I am very thankful for this opportunity. So thank you all, and this event will be really successful, and I hope we will to create more such events in the future. So thank you all. And Chimoy sir, do you have?
No, nothing. Just once again, congratulations. All the best. Good night to everyone. See you again next year.
Oh, okay, sir. So I think that's the conclusion of the conclave.
Sir, can we also take a photo? Can everyone turn on the video and take a photo?
Okay.
I request everyone to turn on the video so that we can take a photo.
Where is our speaker? Last speaker. Sandeep.
Sandeep sir.
Yes, sir. I think we can click the photo. Yes. Okay, so I guess I've taken the photo. Okay, so I guess this is the end of this year. So this is AKAPSSC.
Edwin was not there.
Edwin Chaka?
Yes, sir. I had. Yes, sir. Photo no.
Your video is not on.
It was on photo, I think. It's all right. We can take the photographs and add my video.
Different system will show different according to your data bandwidth.
Yes, sir.
Okay, so
yeah.
This
you can conclude the event.
Okay. So this is so we have reached the end of the event. I would like to thank everyone who was a part of this and who helped us to bring here. So this is AKAPSSC, All Kerala APS Student Conclave, signing off from 2020. Hope you see us again in 21, and hope you participate in the event. So this is Swapnil, and together with all other chairs of APS societies, signing off until next year. Thank you.
Thanks.
So, good night.
Good night. Good night.
Thank you. Good night.
Good night, Raghavan sir.
Night, everyone.
Namaste, namaste.
Namaste.
Yeah. Okay, you may close the meeting.
Okay.
Sir, thank you very much for the support.
Okay, then good night. We will leave.
Raghavan sir, thank you for coming. And then sir also, thank you for coming today.